Okay, so the atom, chapter 28. Today we'll be talking about the Bohr model of the atom. Well, mostly models of the atom and why the Bohr model of the atom was very revolutionary. So we're going to compare and contrast the nuclear model to the Bohr model. We'll look at different emission and absorption spectra. And we're going to calculate the energy required for electrons to change levels. So the first thing we're going to talk about is the different models of the atom. You guys remember J.J. Thomson and his plum pudding model? I always talk about the plum pudding. Yeah. Okay. Did you know plum pudding is actually more like raisin bread? Yeah. It's weird. Like, why would you call it plum pudding? It doesn't have plums in it, and it's not pudding, it's bread. Okay. So what he said is that he's the one that discovered the electron. So he said that atoms would be a positively charged fluid with negatively charged electrons floating around in it like plum pudding, scattered around it. So let's draw like a little model. This is J.J. Thomson's model of the atom. Positive fluid and negative electrons. So the next person to make progress on the atom was Ernest Rutherford. He directed a beam of alpha particles, which are positively charged particles. They're just pretty much protons for the most part. And he projected them at a thin sheet of gold foil. So some of it went through, which was expected, but some of it deflected. So what must be happening in order for it to be deflected means it must be hitting something positive as well. So he said there was something large, probably at the center of the atom, that was positively charged that's deflecting these atoms. Again, it's not all of them. Most of them went through, but some of them bounced back. You guys have cups? You should go get some cups. Thank you. Makes it easier for me to keep my pacing. I can set this down. Use this. Where do you go? The science store.
My science usually from like kindergarten that's been telling me that thing. Like all my science teachers.
Like this magic science store. It's like the magic school bus. No, it's like the Harry Potter places. They just you have to find them. They're hidden. They're hidden stores.
So you won't tell me where they are.
It's the science catalog. You just order them. I get about 6 catalogs a semester, and then usually throw them all away. How old is that? I don't know. I found it. It's probably older than Macy's. All right, so here is kind of a picture of the setup, a relative diagram. So you have your proton cannon, positively charged alpha particle cannon, and it shoots it at this gold foil. And most of these particles go through. So all of this is sensors that go around. And as you can see, these protons are hitting something positively charged somewhere in there and causing them to deflect. So what Rutherford said is he came up with the nuclear model. And with his nuclear model, he said that the center of the atom must be made up of positively charged particles. And then these electrons must be around it somehow. This is my atom. There you go. Nice boring atom. So we're getting closer. So the nuclear model is saying that it has a nucleus. Now he did a little bit of math and he found out that there's something missing. Because we know the mass of an atom. He knew the mass of a gold atom. He knew the charge was neutral, so however many electrons must be that many protons, because he knew how many electrons were in it. So there was some sort of mass missing. Because when he added this stuff up, for instance, if we look at our atom here, we have 2 protons and 2 electrons. And when we add that up, it doesn't equal the mass of this atom. So there's something else in here. And he called that a neutron. And he said that these neutrons and protons were bound together in the center of the atom. Put my neutron in here. Neutron, we'll make it a little dot for a 0, neutron. That made up for that extra mass. And this led to the nuclear model. And this also led to the strong nuclear force, which you would think you have 2 protons next to each other, they would fly apart because they're the same charges. Opposites attract, like repel. So there must be some sort of force holding these protons together and holding these neutrons together, which he called the strong nuclear force. Keeps the atom from flying apart. If we didn't have the strong nuclear force, everything would just be an atomic explosion. So this nuclear model was pretty good at explaining things. It did a good idea, a good job of kind of giving us an idea of what the atom looked like. Except for emission spectra. So they had to figure out how could this atom, because they knew this was good so far. We know protons are in the center. We know electrons are on the outside. We know neutrons are in the center. How come when light is heated up, it emits a spectrum? So you guys remember when we had the diffraction glasses on? The little yellow glasses, which I'm going to pass out again because they're fun. I have a record. Everybody not get them? Okay, so you remember when we put these on and you look up at the lights, you see a spectrum, right? Well, if I turn on a fancy light, like this, which I'm going to do it for you in just a second. For instance, a neon light, we heat up a neon light. Let's say it just has neon in it.
You can try it.
This energy goes through it and it excites the electrons. Now, if this was true, the electrons would continue to emit a whole spectrum. So just like when you look up there. But when we do it for a specific element, only specific lines are emitted. And this is strange. This didn't follow the nuclear model. So we need to figure out what model would. So let's look at a couple of these things. You're going to see some emission spectrums. Yes?
Is that why the light's lower?
What
In colors?
What light is lower?
When we're looking at these, the light's not up there, it's right here.
Oh, it's because it's spreading it out. Each light wave is being diffracted, so it's being bent and spreading out, just like a prism. So the prism spreads the light out, so that's why it's to the side. All right, so this is what we will see, this emission spectrum. This is for a couple of different ones. I think this is a sodium. No, it's not sodium. It'll be for a couple of different ones, maybe hydrogen and helium is probably what this is. So you'll see these little lines in the spectrum. So let me show you what those look like. I don't know if these all work. This one is helium. I'm going to turn the light off, so just give me 1 second. There you go. So I want you to look at this light. This is helium. So helium atom is being emitted and being excited until it has enough energy to emit light. All right, let's look at another one.
This might be a weird question, but why does it make a rainbow if it's just red light coming off of that?
The spectrum, because each atom is emitting its own photon. That's why they're saying this model, this nuclear model, doesn't match. It doesn't work. It's getting there, but it's not there yet. All right, let's look at neon.
Miss Wells, let me see a rainbow right now. Is that coming from the light outside?
Yeah. This one looks like this same one. So the other one wasn't helium then. Someone put in the wrong thing. Okay. All right, what else we got here?
What is that?
Oops. Huh?
The little curly things.
I'm not sure what you're talking about.
In the light when we see it. There's little curly things in the light.
Some type of filament, I think. Okay, this one should be hydrogen.
You'll see it? Oh, I've got like...
Okay, fancy hydrogen.
Hee
That one is.
Oh, it has teal.
I like that one.
I like that a lot.
They're heating up pretty fast. Okay, this one says helium on it, so it might actually be helium. Oh, it even has a sticker on it that says helium. So let's show you what actual helium looks like. That's better. That's helium.
That one is.
So it looks like she's holding 4 of those things.
Notice that each spectrum is different. That means each atom, so I'm telling you what the atom is, emits its own specific spectrum. Let's see, what else do I have? This one says argon. Let's see if it's right. Ooh, that one's pretty.
That one's the.
It's very light.
Anything?
Oh, I see lines in the background.
It's only on the top and bottom.
Yeah, it's on the top.
You see it?
It's like bottom row.
I see lines all over.
And this one's mercury. Ooh, fancy. Just don't break it, right?
The song.
I think mercury is like one of my favorites. Oh, that one's weird. And what's we got? Something about blue tape. Neon. That's another neon. Okay, so those are all the ones that I have. So you can see that each atom emits its own specific spectrum. And that is called an emission spectrum. Because you're heating up the light, you're heating up the gas, and it's emitting its own light, its own spectrum. So now, we'll talk about absorption spectrum. Absorption spectrum is the opposite. You have light, for instance, the fluorescence up there, and it goes through a cold gas, for instance, the oxygen in the room, and some of those lines, those exact same lines that are emitted from oxygen, will be absorbed. Because that oxygen gas is absorbing the same photons that it would emit. This is how we know that the sun is made of hydrogen and helium. Because when we look at the sun outside with our little diffraction glasses, maybe not these ones, but a better one, you'll see the absorption spectrum for oxygen, nitrogen, hydrogen, and helium. But there's no hydrogen and helium in our atmosphere because they're too light. They are not held down by our gravitational pull. So the hydrogen and helium must be in our sun. This is how I believe helium was discovered. It was either helium or hydrogen, but I think it was helium. right, so here's a picture of an absorption spectrum. And this is the one from the sun. So you can see some of these dark lines in there. That's an absorption spectrum. So this one is the emission spectrum for sodium. So this is, you heat up sodium gas, and it's going to emit these two things. So you look at it with your diffraction glasses, and you see the two lines. Now, if you put sodium gas, cold sodium gas, in front of a light, this is what the spectrum looks like. So the light emits the whole thing, and the sodium gas takes out the exact same wavelengths that it would emit. So emission, absorption. All right, this leads us to the Bohr model. We need to put the nuclear model with this emission absorption spectrum. Because right now this model states you heat up the electron, right? You give it energy enough to emit light. It should emit a full spectrum. But what we find is it's only emitting specific wavelengths. So why is it only emitting specific wavelengths? And that leads us to the Bohr model. So Rutherford came up with the nuclear model, which led to the planetary model. So they said that the electrons just orbit in circles. But you guys have been through chemistry. You know that they don't orbit in circles. They orbit in S and P and D and H orbitals, right? So all of that goes back to chemistry. You don't need to know that for this class. We're just going to call them energy levels 1, 2, 3, all the way up. So you don't need to know the shapes of them or the electron configuration. You already know that from chemistry. We're just going to build on it. So this planetary model, which is very simple, didn't really work for these spectrums because they're not just orbiting. They're in orbitals. So this picture of an atom is actually wrong. It's useful for us to imagine it, but it's not correct. So we have to take this model, we have to take the emission spectrum and come up with, and on the next slide I'll show you the Bohr model. The Bohr model united the nuclear planetary model with these different levels, with Planck's quantized energy levels. We talked about photons yesterday. And these emission spectrums. So what he said is that electrons, to jump to the next energy level, can only take the exact packet to that energy level. So if you have an electron in its ground state, let's call this level 1, and we take this electron up to the next state, level 2, let's say to get to this level, it's 10 joules of energy. So the photon hitting it has to be exactly 10 joules. You can't break the photon up. So for this particular atom, it is only going to absorb photons with 10 joules of energy. And if it was sodium, then it would be that specific wavelength of light, that little tiny yellow sliver. If it's 13, it's going to ignore it. If it's 8, it's going to ignore it. It can only absorb 10 joules. Sorry, this is a J. I know that was fun. So when it's absorbing light, an absorption spectrum, the full spectrum's landed on it, and it's only going to absorb the part that has the photon for 10 joules. So that's why only that sliver is taken out. And if it's emitting light, we are adding energy into this electricity to excite it up to level 2. And when it's here, when the electron's here, it's going to drop down. And when it drops down, it emits a photon of 10 joules. And that's why when it's emitting, it only emits that particular photon, because that photon has to have 10 joules, because that is right here as it drops down. So this takes care of the quantized energy. This Bohr model of the atom took care of the emission spectrums. It said that electrons have to be in specific energy levels. They can't be halfway up. They're either on ground state, they're either in level 2, level 3, level 4. They can't be at level 1.5. So they have to only absorb that specific packet of energy with exactly 10 joules. Now, it's not going to be 10 joules in real life. That's just an example. It will have its own specific energy. So the first state that the electron is in is called the ground state. So level 1 is always ground state. And if you get that perfect packet of energy, we can give it to the electron to get to the next level. Remember, in this example, it has to be exactly 10 joules. And when the electron loses that energy, which it does spontaneously because it gets its energy, it gets into the excited level, let's say level 2, it's all excited, but it gets tired pretty easy, it doesn't like to party that much, and it will drop back down to its ground level on its own. It's called spontaneous. It spontaneously drops down to the ground level. It's called spontaneous emission. And since it does it by itself, it will emit a photon when it does this. So when it does that, it'll emit a photon, and in this example would have an energy of 10 joules, which would have a specific frequency, and if this was sodium, it would be a yellow beam. All right, so let's look at some of the equations for this. Now, this one I gave you yesterday, so it shouldn't be new. I just put it back up there because you're going to use it in your homework. And this is the energy of a photon is equal to hf. Now, if you're talking about the atom, the electron itself might have an energy level, so you have to go like N2, N3, depending on its energy level. But we're saying here the photon that enters into this atom is going to be the same amount of energy that that electron is gaining. So the change in the energy of the atom, because you've added it to that electron. This is Planck's constant, or Planck's constant, right here at 6.63 times 10 to the negative 34. So if you're given frequency or joules, you'll use this stuff. You're given wavelength, make sure your wavelength is in nanometers, and it will give you energy in electron volts. So depending on what you're given, you can use either one. And then I have this one last equation from chapter 15 here. Just to remind you, wavelength is equal to velocity over frequency, so if you need to convert between the two. And the speed, the velocity of light is always 3 times 10 to the 8. So you know that number. All right, here's some pictures, because I know how you guys like pictures. So we have the nucleus, and we have our electron in the ground state where it likes to be. So a photon, or a spectrum of light that comes in, this electron will absorb this amount of energy, this amount of energy, this amount of energy, or this amount of energy. Obviously, the higher it gets, the more energy it requires. It will also absorb, if it's already in the second state, it can absorb this amount of energy, this amount, or this amount. Think of it the other direction. If it's giving off energy, so it's being excited and then giving off, emitting, it can give off the photon for this, 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 all the combinations possible. So each energy is going to correspond, each level is going to correspond to a different energy, and it could be 2 levels. And that's why when you look at like hydrogen, you don't just see one line, you see multiple of them, because there's many different combinations you can have. Which means that the higher up your atom is, with more electrons, the more variety of levels it can be excited to. So here's another picture for you. If the electron in this one is excited from the ground state to state 3, it will absorb this much energy. And when it goes back down, it will emit the same photon. Now, it can be excited to level 2 and emit that photon when it goes back down, or it could be excited from 2 to 3, and when it goes back down, it will emit that photon. So it only absorbs the wavelengths that correspond to that. Okay, I don't want you to write this equation down, I just want to show it to you. I'll have you write the next one now. This is the radius of the electron around the hydrogen atom. This only works for hydrogen. So the Bohr model only works for hydrogen. Boom. This is, again, the radius, so from the nucleus out to the electron. Let's draw that picture real quick. So from here to here, r, radius. H is Planck's constant. N is the energy level. So if it's a ground state 1 or if it's ground state 2, it's going to be further away. Down here, 4 pi squared K, 9 times 10 to the 9. It's a constant. Mass of an electron, because we're talking about the electron, so that's a constant. And Q, charge of an electron, which that's a constant. So pretty much everything in here is a constant except for this energy level. So instead of writing this equation, I want you to write this equation for your homework. So we can find how far away this electron is from the center of the atom just by knowing its energy level. So if it says ground state, we put 1 in. If it says it's on level 5, then we put 5 in. So N is your energy level. I got one more slide and then we got quick questions. Oh no, this is the last one. Then I have quick questions. Now stuff down here is, since we know Planck's equation, right, E equals NHF, and we know this radius, we now can tell you how much energy each level has. With all of those constants put together, if you need to know the energy in joules, you use this equation. And again, this is energy level. If you need to know it in electron volts, you use this equation with its energy level. So nice, simple, easy equations. Much better than the first one I showed you. All right, here is clicker question number 1. After bombarding metal foil with alpha particles, the Rutherford's experimental results led him to conclude that the positive charge of an atom is where? I'll give it a second, it's still loading. All right, it should work now.